Okay, let's unpack this. Today we're taking a deep dive into a truly fascinating and highly anticipated new paper, Gated Delta Networks, Improving Mamba2 with Delta Rule. Now, for those of you deeply immersed in the world of machine learning, data science, advanced mathematics, you're acutely aware that the quadratic scaling issues of traditional transformers, especially with their self-attention mechanism, well, they remain a persistent bottleneck. This challenge impacts everything, right? From training massive large language models to deploying them efficiently for long context inference. This paper doesn't just propose an incremental fix, it offers an innovative solution that truly pushes the boundaries of what we can achieve in efficient sequence modeling. Our mission for this deep dive is to comprehensively explore the concepts, the underlying mathematical ideas, and of course, the empirical results presented in this paper. We want to extract the most important nuggets for your expert understanding. We really want to understand not just what they did, but why it matters so profoundly.
Absolutely. And what's fascinating here, and indeed what the paper addresses head on, is the inherent limitation that has plagued both traditional transformers and their linear recurrent neural network alternatives, the RNNs, particularly when dealing with long context and retrieval tasks. I mean, while transformers certainly excel in precise, non-local sequence modeling, they can capture dependencies across vast distances in text, which is amazing, and they beautifully leverage the parallel processing power of modern GPUs during training. Their self-attention component, the part that scales quadratically with sequence length, well, it's a computational beast. No other way to put it. This leads to substantial demands on both memory and processing power. It creates a significant hurdle for training and inference, especially as models and contexts grow, to the scale of millions of tokens. So linear transformers, on the other hand, emerge as a really promising avenue to mitigate this. They essentially reframe attention as a linear RNN. This dramatically reduces memory requirements and offers linear scaling during inference, which is huge. But the early versions often underperformed in key areas, notably language modeling, compared to their traditional counterparts. They really struggled to maintain critical information over extended sequences. This really raises a fundamental question for us. How do we get both? How do we achieve the efficiency of linear scaling and the powerful performance needed for sophisticated information management over long sequences? The authors of this paper made a critical observation here. Two distinct mechanisms, gating and the delta rule, which we'll definitely explore in detail, offer highly complementary strengths in memory control. And their synergistic combination, as we'll discover, is where the true innovation in gated delta networks lies.
It's incredible how many layers of ingenuity go into tackling just one part of this monumental problem. It really is. So picking up on that, to truly appreciate the gated DeltaNet, we probably need to quickly unpack its two intellectual predecessors, Mamba2 and DeltaNet. You mentioned early linear transformers, while offering undeniable efficiency benefits, consistently ran into pretty significant issues with long sequence information management. It wasn't just about speed, was it? It was fundamentally about memory. You describe it like a memory collision problem, where the number of orthogonal key-value pairs they can actually store is fundamentally bounded by the model's dimensionality. So when the sequence length exceeds this dimension, memory collisions become an inevitable hindrance for exact retrieval. Information starts to bleed together, making precise recall difficult. So from your perspective, what mechanisms were introduced to specifically overcome this inherent limitation? How did they attempt to manage this memory challenge in these earlier linear models?
That's a crucial point, yeah. And it really highlights the challenge Mamba2 and DeltaNet set out to solve, but from different angles. Mamba2, as the paper describes it, introduces a rather clever gated update rule. It attempts to address this memory collision problem by allowing for a form of, let's say, controlled forgetting. Its recurrence relation is defined as 8tt bop st1 plus vt kt top. Okay, so here, AT represents the state at time, which you can think of as the accumulated memory, are the value and key vectors for the current time step, basically the new piece of information to be integrated. The crucial element, though, is alpha. It's between 0 and 1, and it's a data-dependent scalar decay term. What this term does is it uniformly decays all key value associations stored in the state at each time step. Effectively, older memories fade out proportionally. Now, what's particularly significant, especially for this audience, is that this recurrent formulation has this powerful equivalence with a parallel form. Think like ODE at gamma, where O is output, Q, K, V are query key value matrices, and gamma handles the cumulative decay. This equivalence between recurrent and parallel forms is a really significant concept. It's known as state-space duality. And it's critical because it allows us to train these conceptually sequential recurrent models with the efficiency of parallel matrix operations on our modern GPUs. It beautifully bridges the gap, between how we intuitively think about time series data and how we computationally process information on hardware optimized for these huge matrix multiplications, we've seen this duality in other architectures too, like gated RFA and XLSTM. It underscores its mathematical elegance and, importantly, its practical utility in scaling recurrent designs.
Okay, so state-space duality is key for the parallel training. Makes sense.
Exactly. However, while Mamba2 proved quite effective in language modeling, its limitation becomes pretty apparent when you consider memory utilization in tasks needing precise recall. Because it uniformly decays all key value associations with that single outfit, it doesn't account for their varying importance. So if you need to selectively forget just one specific piece of information or retain another with super high fidelity, well, everything gets forgotten equally. It's like having a whiteboard where all the writing just fades simultaneously. You can't erase just one specific sentence without everything else also dimming. This leads to potentially inefficient memory management, the difficulties in targeted retention. It makes it a rather blunt instrument for highly nuanced memory tasks.
A blunt instrument, okay. So effective for general fading, but not surgical.
Precisely. And the paper also details the hardware-efficient chunk-wise training algorithm for Mamba2. This approach is absolutely critical for practical, large-scale training. You just can't do it otherwise. It splits inputs and outputs into chunks, usually size C. The state update, something like ST plus 1 plus VTOPT, and the output calculation, over left T S topped gamma, these are meticulously engineered to be heavily optimized for tensor core GPUs. This optimization relies on reframing the operations as matrix multiplications, which are, the bread and butter of modern GPU tensor cores. Those arrows, like vect_st, they indicate variables decaying across the chunk to the first or last position. For example, vect_st means the state matrix decays over the entire chunk. These reformulations aren't trivial. They specifically exploit mixed precision capabilities, fused operations of tensor cores, allowing for incredibly high throughput by keeping data paths busy, and minimizing memory fetches. Without this kind of deep hardware-software co-design, the theoretical efficiency gains of these linear RNNs would just evaporate in practice.
So Mamba2 offers this powerful general decay, a kind of elegant fading memory. But as you said, it sounds like a blunt instrument when you need precision. What if you need to perform more surgical operations on your memory? What if you need to remember one specific detail while letting other things fade, or even replacing one specific detail with a new one? How does DeltaNet approach that memory management differently? With more finesse, perhaps?
That's precisely the philosophical shift DeltaNet introduces. Yeah, finesse is a good word for it. In contrast to Mamba2's uniform decay, DeltaNet, based on the Delta update rule, takes a fundamentally different surgical approach to memory modification. Its update rule is given by Haytake ST1 I betat KT KT top. Now, this formulation dynamically erases the old value associated with the count key, and then writes a new one, the ATT top. And it does this based on a writing strength, also between 0 and 1. It essentially implements a first-order linear recurrence with what are called generalized householder transition matrices.
Householder matrices. Okay, that sounds specific. Why those?
Good question. What's particularly fascinating here, especially for those familiar with numerical linear algebra, is the choice of householder matrices. They aren't just arbitrary. Their orthogonal properties are precisely what allows for a clean, targeted update and erasure of specific information. Conceptually, you can think of it like a geometric transformation. It rotates out an old vector associated with a key and rotates in a new one, crucially, without disturbing other memory components. This gives DeltaNet its remarkable ability to selectively update memory by replacing an old key value pair with an incoming one in a sequential, precise manner. And this method has shown really impressive performance in synthetic benchmarks, particularly for in-context retrieval tasks where exact recall of a specific item is paramount. It's far more targeted than the broad-stroke decay of Mamba2.
So much more precise, like a laser scalpel compared to Mamba2's wide brush.
Exactly. However, DeltaNet has its own inherent limitations, which become clear when we move beyond those synthetic tests. Since it only modifies a single key value pair at a time, it severely lacks the ability to rapidly clear outdated or irrelevant information on a larger scale, especially during context switches. Imagine an LLM switching from discussing, say, quantum physics to talking about baking recipes. DeltaNet would struggle to quickly flush the memory related to quantum physics. It'd be like trying to clean a crowded whiteboard by erasing one word at a time, incredibly inefficient for a global reset. So this absence of a robust, rapid memory clearing mechanism means that while it's excellent for precise updates, it can lead to memory saturation. New information starts overwriting or colliding with other relevant stored data because the state size is fixed. This inherent limitation contributes to only moderate performance on many real-world tasks, despite its strengths in selective updating.
Right, so it can get cluttered easily if the context changes dramatically.
Oh. Precisely. And similar to Mamba2, DeltaNet also utilizes a hardware-efficient chunk-wise parallel form for training. The paper describes the partial expansion of its recurrence, which involves cumulative products of these generalized householder matrices. This is where specialized numerical linear algebra techniques become critical again. This complex expansion is optimized by using the classical WY representation. That's a block form allowing efficient representation of a sequence of householder transformations and the UT transform. These techniques are designed to refactor the complex recurrence into a series of matrix multiplications highly amenable to GPU tensor core optimization. The state update becomes ST+1 and the output is OT top keyword top. Both of these are meticulously designed for tensor core GPUs, ensuring that while the underlying rule is mathematically more expressive and complex, its implementation remains practically efficient. This is a non-trivial engineering feat, allowing the model to leverage batch processing and optimize kernels despite its sequential nature.
That's a truly deep dive into the mechanisms. Okay, so let me recap quickly. On one hand, we have Mamba2 with its effective data-dependent gating for generally forgetting history, excellent for shedding irrelevant context, but not to precise recall, a broad cleaner. And then we have DeltaNet with its precise selective memory updates, great for target association and overwriting, but lacking a mechanism for rapid, broad memory clearance, a surgical instrument. It sounds like we have two incredibly powerful yet almost diametrically opposed approaches to memory control. How do you even begin to merge something that broadly decays with something that precisely updates? What was the most significant aha moment the authors likely had when realizing these two concepts weren't competing, but truly complementary? And from your perspective, what was the biggest hurdle in actually fusing them mathematically into the gated DeltaNet?
That's precisely the central insight of this paper, yeah.
Mm-hmm.
And it's a testament to the author's deep understanding of memory architectures. The aha moment likely stemmed from recognizing that the limitations of each model were precisely the strengths of the other. It's quite elegant, really. Mamba2 provides that global data-dependent forget gate needed for dynamic context switching. DeltaNet offers the precise surgical memory modification crucial for accurate in-context retrieval and fact retention. They aren't mutually exclusive. They're two sides of the same coin when it comes to sophisticated memory management.
Okay, so seeing the weaknesses as complementary strengths.
Exactly. The biggest hurdle in fusing them mathematically would have been maintaining the hardware efficiency and parallelizability that make these linear models attractive in the first place, especially given the increased complexity. You can't just stack them right. You need a unified rule that integrates their functions seamlessly within a single recurrence. And that leads us to the proposed rule, which is a powerful fusion, combining the strengths of both approaches into a single, elegant recurrence relation. Plus betat vt ata top plus betat vt apa top. In this formulation, you can clearly see the data-dependent gating term, alpha from Mamba2. But now this term intelligently modulates the entire selective update mechanism from DeltaNet, along with its writing strength. The genius of this unified rule lies in its incredibly flexible memory control. Think about the practical implications for an LLM. Need to rapidly switch contexts. Set alpha to 0. This promptly clears the model's entire memory, discarding outdated stuff, crucial for maintaining focus. Need precise, targeted updates. Set alpha to 1. The rule effectively switches to the pure delta rule, enabling highly selective updates without affecting other stored info. Invaluable for in-context learning or recalling specific facts.
Wow, okay, so that alpha becomes like a dial, controlling whether you're in broad forget mode or surgical update mode or somewhere in between.
Exactly. This dynamic ability to both broadly forget and precisely remember is a conceptual leap. It means a fundamentally more adaptable memory system. It can mimic both rapid conceptual shifts and precise fact recall, something previous linear models really struggled to do simultaneously without big performance trade-offs. And connecting this to the bigger picture, the paper formally analyzes this through an online learning framework. It draws on recent work interpreting recurrent state updates as closed-form solutions to online learning problems. As shown in Table 1, Gated DeltaNet's online learning objective is ST1 wrangle, maintain wrangle, if DT alpha ST1 wrangle. This objective is particularly insightful because it highlights how introducing this adaptive scaling factor effectively relaxes the regularization term present in many linear RNN objectives. This relaxation allows for controlled deviations between the one, which is exactly what enables dynamic memory management through selective forgetting. Without this relaxation, models might saturate their states, making retrieval hard due to memory collisions, like we discussed with DeltaNet. The alpha term acts like an intelligent governor, preventing memory overload while still allowing targeted modifications.
That's fascinating, connecting it back to online learning and regularization.
Yeah, and from a fast-weight programming perspective, where you think of as a fast-weight matrix updated at test time, the delta rule inherently optimizes an online regression objective via test time SGD. The gated delta rule can then be viewed as incorporating an adaptive weight decay term alpha into this SGD update. This isn't just theoretical curiosity. Adaptive weight decay is a technique widely used and proven effective in deep learning to prevent overfitting and improve generalization. By bringing this concept into the recurrent update rule, the authors provide a strong theoretical underpinning for Gated DeltaNet's design choice. It connects it to established regularization techniques. It's a very elegant synthesis, really.
That's an incredibly elegant fusion, truly synthesizing the best of both worlds in a single, powerful recurrence. But, as you mentioned earlier, mathematically integrating these two distinct mechanisms while maintaining hardware efficiency must have been a Herculean task. The theoretical formulation is one thing, but translating that into something that runs effectively on modern GPUs, particularly at scale, that's a whole other challenge. How did the authors navigate the engineering complexities to ensure this powerful rule could be trained efficiently?
You've hit on one of the most critical aspects of this work, yeah. Bridging that gap between theoretical elegance and practical deployability. The remaining challenge, naturally, was ensuring this innovative gated delta rule could be implemented in a hardware-efficient manner, especially for large-scale training where every FLOP and memory access counts. The paper addresses this by extending the efficient chunk-wise training algorithm, originally developed for DeltaNet by Yang et al., to seamlessly incorporate the new gating terms. The core idea is to adapt the partial expansion of the recurrence for gated DeltaNet. Now, this expanded form, which needs calculating in parallel over chunks, becomes quite intricate. Breaking this down, you see cumulative products of matrices. Each matrix itself is a mix of scalar decay and a householder-like transformation. Direct computation for every step within a chunk. That would quickly become computationally intractable.
Right, that looks computationally very heady if you do it naively.
Exactly. So this is where the derivation meticulously adapts those advanced techniques from numerical linear algebra, the WY representation and the UT transform. As we touched on, the WY representation lets us represent a sequence of householder transformations efficiently as a product of simpler matrices. Ideal for batch processing on GPUs because it turns sequential operations into larger, parallelizable matrix multiplications. The UT transform helps handle the upper triangular structure that emerges. By leveraging these specific techniques, the authors refactor the computationally intensive parts into matrix multiplications, perfect for tensor core acceleration. This ensures that the increased mathematical complexity of the gated delta rule doesn't come at the cost of practical training speed.
So clever numerical tricks save the day for efficiency.
Essentially, yes. The resulting hardware-efficient chunk-wise algorithm for gated DeltaNet is then given by two key equations, mirroring the structure we saw before. For the state update across chunks, st plus 1 is top plus over left arrow vest m, and for the output calculation within a chunk. These equations use the same chunk-wise decaying notations of those arrows indicating decay as Mamba2. This consistent optimized approach is not just an implementation detail, it's a critical bridge between theory and practice. It allows gated DeltaNet to preserve chunk-wise parallelism and be trained efficiently, circumventing what could have been a major bottleneck. Without this deep hardware-software co-design, the elegance of the gated delta rule might have remained purely academic.
With the theoretical underpinnings and the clever engineering for efficiency now crystal clear, the real test, of course, comes down to empirical validation. The authors performed a comprehensive suite of experiments comparing gated DeltaNet against a wide array of state-of-the-art architectures. My immediate thought when reviewing the experimental setup was how rigorous it seemed. What aspects of their experimental design really stood out to you as most rigorous or potentially revealing for our expert audience?
That's a great observation. The rigor of their experimental setup is indeed a highlight. It lends significant credibility to their findings. What stood out was the meticulous control. All models scaled to 1.3 billion parameters, trained on a substantial 100 billion tokens from FineWeb Edu, used Atom-W, cosine annealing, Llama-2 tokenizer, identical conditions. This commitment to uniform conditions is paramount because it isolates the architectural differences as the primary variable. It allows for a truly fair comparison across a diverse set of models, and the lineup was comprehensive, right? Pure transformers, various RNNs like RepNet, HDRN2, Mamba2, DeltaNet, even hybrid models like Samba. This breadth is important. It shows where the new architecture stands not just against its direct predecessors, but across the broader landscape. The evaluation was equally comprehensive. Language modeling, common sense reasoning, in-context retrieval, synthetic and real world, length extrapolation, long context understanding. This thoroughness ensures they didn't just cherry-pick tasks where Gated DeltaNet would shine, but tested its generalized capabilities across the spectrum of LLM functionality.
Okay, that sounds robust. Now, the SNIAH benchmarks, single needle in a haystack, they're always particularly telling for memory and retrieval and long context. They really highlight fundamental differences. What were the most striking aha moments you saw in these synthetic tests that truly confirmed the hypothesis of the gated delta rule synergy?
Oh, absolutely. The SNIAH suite vividly illustrates the complementary strengths in action. Those aha moments really pop out when you look at Table 2 in the paper. Take SNIAH1, the passkey retrieval. This tests long-term retention of one specific item with minimal, repeated synthetic context. The results were stark. DeltaNet. Near perfect performance across all sequence lengths, like 99.9% at 8K, shows its exceptional strength in memorizing specific associations. That's its superpower. Mamba2, though, degraded significantly beyond 2K sequences, plummeted from 99.2% at 1K down to just 30.4% at 8K.
Wow, quite a drop.
A huge drop. It highlights the drawback of uniform decay perfectly. If you're constantly washing away the entire whiteboard, finding that one crucial piece of info gets incredibly hard. Gated DeltaNet, with its blend, showed much less severe degradation. It achieved 91.8% at 8K. This resilience is a direct testament to the delta rule's role in retaining information more precisely, even under the influence of the gating term. It confirmed that precision could coexist with some decay.
Okay, so DeltaNet hold on perfectly. Mamba2 forgets too much. Gated DeltaNet finds a strong middle ground.
Exactly. Now, moving to SNIA2, numerical needle, and SNIAH3, UID needle with real context. These test efficient memory management when storing relevant info amidst lots of noise with a fixed state size. Here we see a different dynamic, really revealing the gating's role. DeltaNet's performance dropped significantly at longer sequences. In SNIH2, it went from 98.4% at 1K down to a dismal 14.4% at 8K.
Why such a big drop for DeltaNet here?
It's primarily due to poor memory clearance. With a fixed state size and no effective way to flush irrelevant data, memory collision becomes rampant. It's like having limited sticky notes. If you never remove old ones, new important notes just get covered up or lost. Mamba2 and Gated DeltaNet, by contrast, maintain much better performance through their gating mechanisms, which effectively filter irrelevant information from accumulating. For instance, in SNIH2, Mamba2 was at 56.2% at 4K, but Gated DeltaNet was at an impressive 92.2%. And in SNIH3, with more complex UIDs and real-world context, Gated DeltaNet actually outperformed Mamba2, achieving 84.2% at 2K compared to Mamba2's 47.6%. This verifies the delta rule's superior memorization ability even within a more complex filtered context. These results clearly demonstrate the synergy, gating for dynamically filtering and clearing out the irrelevant haystack, and the delta rule for precise, targeted memorization of the needle within that managed memory. This is the conceptual leap, simultaneous rapid conceptual shifts and precise fact recall without those massive performance trade-offs.
Those synthetic results are compelling. They really break down the mechanistic advantages nicely. But the real test for any LLM architecture is how it performs on general language modeling tasks in complex reasoning, where the demands are far less constrained, more indicative of real-world utility. How did Gated DeltaNet fare in these broader measures?
Right. Moving beyond those insightful synthetic benchmarks, the paper presents compelling results in more generalized real-world tasks. It validates the architecture's broader applicability. As shown in Table 3, Gated DeltaNet consistently outperformed other linear models across both 400M and 1.3B parameter scales. This was seen in crucial metrics like language modeling perplexity and zero-shot common sense reasoning accuracy. For example, in language modeling, Gated DeltaNet achieved a wiki perplexity of 16.42. That's notably lower, so better, than Mamba2's 16.56. Similarly, its LMB perplexity of 12.17 compared favorably to Mamba2's 12.56. In common sense reasoning, it achieved an average accuracy of 55.32%, which was slightly but consistently higher than Mamba2's 54.89%. Now, these aren't massive leaps, perhaps, but they demonstrate consistent, meaningful improvements. This indicates its improved ability to handle complex reasoning tasks, generate more coherent language, and ultimately make better sense of information. It shows the superior memory management translates not just to retrieval, but to a richer understanding and generation of text. It's not just memory, it's the utilization of that memory in complex cognitive tasks.
And real-world retrieval is often the acid test, isn't it? Given the inherent needle and haystack challenges of extracting specific facts from lengthy, often noisy, real-world documents, how did Gated DeltaNet stand up in these recall-intensive scenarios, which are so crucial for many practical applications of LLMs?
You're absolutely right. Real-world retrieval tasks, with their noise and varied contexts, often expose practical limitations more thoroughly than synthetic ones. Looking at the results for in-context retrieval on real-world data presented in Table 4, the picture becomes even more nuanced and instructive. Pure recurrent models, as expected perhaps, due to their fixed state size and general architecture, still showed a performance gap compared to powerful transformers in these tasks. This suggests there's still work to be done for linear models to fully match transformers' raw retrieval power in all scenarios. However, Gated DeltaNet significantly closed that gap amongst the recurrent models. Interestingly, DeltaNet, despite its superior performance in synthetic retrieval like SNIH1, actually lagged behind Mamba2 in real-world retrieval.
Well, that's surprising. Why would that be?
It underscores a crucial point. The ability to robustly clear irrelevant memory is often more important in messy real-world contexts than just precise, targeted updates. Without an effective global flush, memory saturation can quickly degrade performance when the input stream is diverse and constantly shifting focus. The real world is messy. Gated DeltaNet, through its unified rule providing both selective update and global decay, outperformed both DeltaNet and Mamba2. It achieved an average accuracy of 30.6% compared to Mamba2's 29.8% and DeltaNet's 26.2%. Now, the paper attributes the smaller improvement margin here relative to the dramatic gains in SNAH to issues like repetition errors. These are common in smaller, instruction-unaligned LLMs and often largely independent of the specific memory update rule. So these systematic errors might be dampening the observable differences in these broader benchmarks. It suggests that while the memory mechanism is improved, other architectural components or training methods might be needed to overcome such errors.
That's a comprehensive picture of its capabilities on standard benchmarks. Very insightful. But for truly next-generation LLMs, the ability to scale to truly long context without degradation is, well, it's a holy grail. We're talking about contexts far exceeding typical training lengths. How did Gated DeltaNet hold up when pushed to its limits in length extrapolation and long context understanding?
Indeed, length extrapolation is a litmus test for the robustness of a model's memory architecture. It really shows if it can generalize. For length extrapolation on long sequences, Figure 2 in the paper showcases performance on sequences up to 20K tokens. This is across 6 demanding long context benchmarks, like GovReport, QMSum, CodeParrot. Gated DeltaNet achieved the lowest overall perplexity among all RNN models evaluated. It consistently demonstrated more robust memory management. This is significant because it indicates the model's ability to maintain performance and effectively use information even as context length increases dramatically beyond what it might have seen during training. It implies a deeper understanding of how to manage its internal state without succumbing to memory limits or information decay over extreme distances.
So it generalizes well to longer sequences? That's a big plus.
Definitely. And furthermore, in long context understanding tasks from Longbench, detailed in Table 5, Gated DeltaNet again showed consistent advantages. This was particularly evident in single document QA, few-shot in-context learning, and code tasks areas where robust state tracking and precise retrieval are absolutely paramount. For example, it achieved an average accuracy of 16.6% across these diverse tasks, significantly surpassing Mamba2's 13.5% and DeltaNet's 13.6%. These results translate to superior capabilities in retrieval, in-context learning by leveraging provided examples, and accurate state tracking for tasks like code completion or debugging. These findings collectively paint a picture of a more capable and generalizable model that can truly leverage extended context effectively.
Okay, better performance across the board, especially in long contexts. But what about speed? Does this added complexity hurt throughput?
The efficiency question. Always crucial. As shown in Figure 3, the proposed gated delta rule introduces only a marginal overhead compared to DeltaNet. Gated DeltaNet achieved essentially the same training throughput as DeltaNet. Both are slightly slower than Mamba2, maybe by about 2-3K tokens per second. This is an expected and frankly understandable trade-off due to their more expressive transition matrices. The gated delta rule is just doing more intricate computations per token than Mamba2's simpler diagonal decay. This increased mathematical complexity naturally incurs a slightly higher computational cost per token. However, as we'll discuss next, hybrid approaches often combine these with highly optimized attention kernels to achieve even higher throughput. It shows the performance gains are well worth the marginal manageable efficiency trade-off, and that practical viability is still a strong point.
That's a comprehensive picture of its standalone performance, and it's remarkable how much mileage they got out of such an elegant unification. And you might be wondering, as you just touched upon, if gated DeltaNet is so good, why do we even need hybrid models? What are the remaining limitations of any linear transformer that would still warrant combining it with other architectures? It sounds like there isn't a single silver bullet, even with this advancement.
That's an excellent question, and it really gets to the heart of the current landscape in LLM architecture design. You're right, no silver bullet. While gated DeltaNet makes tremendous strides, even with its advancements, linear transformers still have inherent fundamental limitations. For instance, they can struggle with modeling very specific local shifts and direct comparisons between adjacent tokens. Self-attention excels at that. Additionally, while memory has improved, their fixed state size can still inherently hinder optimal retrieval, especially in certain complex, high fan-out scenarios where the number of relevant items could theoretically exceed the state's capacity. This is precisely where the paper introduces hybrid architectures, strategically combining gated DeltaNet layers with other powerful mechanisms to achieve even greater performance and efficiency by playing to each component's strengths.
Okay, so leveraging the best of multiple worlds, how do they structure these hybrids?
Well, the basic gated DeltaNet itself follows the macro architecture of popular models like Llama stacking token mixer layers with Sujio U MLP layers. The key difference is replacing self-attention with its gated delta rule token mixing. Figure 1, right, illustrates this block design. Queries, keys, values, QKV, generated via linear projection, a short convolution to capture local context, which linear RNNs sometimes miss, SILU activation with L2 norm on Q and K for stability. The crucial alpha and beta parameters are generated through just linear projection. This modular design makes it highly amenable to hybrid approaches. The paper proposes two specific hybrid models. First, gated DeltaNet H1. This combines gated DeltaNet layers with sliding window attention, SWA. The intention here is clear. Leverage attention strength for local context modeling, where SWA excels, reducing the memory management burden on the recurrent gated DeltaNet parts. Each component specializes. Second, gated DeltaNet H2. This takes it a step further by stacking Mamba2, gated DeltaNet, and SWA layers. This creates an even more potent combination, seeking to capture a broader range of dependencies by integrating different linear recurrences with local attention.
And do these hybrids actually deliver on that promise of enhanced performance?
They consistently do, yes, across the benchmarks. For instance, in Common Sense Reasoning, Table 3, gated DeltaNet H1 achieved 56.4% average accuracy, H2 reached 56.18%. Both significantly outperform the standalone gated DeltaNet's 55.32%, clear benefits. In real-world retrieval tasks, Table 4, the improvements are even more pronounced. Gated DeltaNet H1, 39.0% HG, and H2, 40.1% VG, significantly outperform not only the pure recurrent models, but also surprisingly surpass pure attention models like Transformer++, 37.0% EG. This demonstrates their superior ability to handle complex retrieval by combining global memory with local precision.
Better performance, even beating some pure attention models in retrieval. What about the throughput for these hybrids?
Crucially, in throughput comparison, Figure 3, these hybrid approaches also maintain compelling training throughput across all sequence lengths, even on shorter sequences. They often outperform standalone mixers. Gated DeltaNet H1, for example, shows remarkable efficiency. This is because they can combine the linear scaling of the recurrent parts with highly optimized attention kernels like Flash Attention 2 for the SWA components, which offer exceptional speed for local attention blocks. Table S22 in the appendix further shows that the specific order of layers matters. The Mamba2 plus gated DeltaNet plus SWA configuration in H2 yields superior results, highlighting the importance of thoughtful architectural design. These hybrid models clearly represent a highly promising path forward for achieving even higher performance and efficiency in LLMs.
So gated DeltaNet is a formidable step forward, and its synergy with hybrid architectures opens up even more possibilities. Zooming out a bit, where does this advancement fit within the grand narrative of linear RNNs and the broader quest for efficient, powerful LLMs? What are the implications for the theoretical and practical landscape?
Looking at the broader implications, Gated DeltaNet sits within a rapidly evolving, really dynamic field of linear RNNs. It's a testament to the community's relentless pursuit of efficient LLMs. The landscape has seen a significant transition, hasn't it? From early models using data-independent decay like S4 and RetNet to more advanced approaches incorporating data-dependent decay like HGRN, Mamba, RWKV. This shift highlights the consistently proven advantages of dynamically controlled gating and forgetting mechanisms. It's a core concept going back to classic LSTMs, but reimagined for parallelism.
Right, the gating idea isn't new, but the parallelizable implementation is key.
Exactly. What's fascinating here is how modern forget gates, unlike traditional LSTMs, are designed to remove the dependency on the previous hidden state, relying solely on input data. This modification is critical because it enables efficient parallelism across sequence lengths, a key requirement for scaling LLMs. The absence of such a robust, parallelizable forget gate was a notable structural deficit in the original DeltaNet, which Gated DeltaNet now addresses naturally, effectively, and crucially in a hardware-efficient way. The paper also notes concurrent work, like RWKV7, using a similar idea but with a more relaxed formalism using diagonal plus low-rank transitions. This convergence across different groups further validates the core principle.
That historical context is crucial, showing gated DeltaNet as a natural evolution. But let's hone in on the core of DeltaNet itself, the delta rule. You mentioned its superior memory capacity compared to Hebbian learning. For an expert audience, what's the deeper significance of the delta rule here, and how does gated DeltaNet push its capabilities further within that theoretical framework?
Indeed, the delta rule itself warrants deeper consideration. It demonstrates superior memory capacity compared to Hebbian learning, which many linear transformers rely on. This advantage is evident across various tasks, from synthetic in-context learning to language modeling, even image generation. From an information theory perspective, Hebbian learning can suffer from interference and capacity limits. The delta rule, by actively minimizing prediction error, achieves more efficient memory utilization. DeltaNet's data-dependent structure, i.e. Bertetti plus low rank, offers significantly greater flexibility than Mamba2's simpler data-dependent diagonal matrices, alpha I. This structural advantage is profound. It enables more complex reasoning and state tracking, potentially extending beyond what's known as TC0 complexity.
TC0 complexity, right?
It's potentially more expressive power. Potentially, yes. TC0 roughly refers to problems solvable by constant depth circuits with unbounded fan-in gates, implying limited computational expressiveness for logic and complex patterns. The delta rule's structure allows for more intricate dynamic state transformations, crucial for applications like code generation, sophisticated math reasoning, or nuanced factual retrieval. Despite these advantages, the pure delta rule faced theoretical limits and showed only moderate real-world performance standalone, as we saw with DeltaNet, suggesting room for enhancement. Gated DeltaNet builds upon advancements aiming to enhance expressiveness without sacrificing parallelism. This includes research into negative eigenvalues or multiple products of householder matrices for high-rank transformations, allowing memory to represent more complex relationships. From the online learning perspective, the paper acknowledges alternative formulations could extend expressiveness further, like nonlinear regression, or considering the entire history. However, these often introduce nonlinear recurrence, needing complex workarounds or approximations to maintain training parallelism. It highlights that delicate balance. Expressiveness, efficiency, and hardware-accelerated training.
Always a trade-off. And what about the future of hybrid models you mentioned?
Right. The paper provides crucial insights there, too. This work explores interleaving hybrid attention layers across different network layers, a strategy becoming increasingly common, used successfully in models like Minimax-01 and hybrid Mamba2 attention. This layered approach allows different mechanisms to contribute specialized strengths at various processing stages. Building a more robust, adaptable system, why not have both local context experts and global memory experts working together? This raises an important question for future exploration, a challenge for the field. What about hybrid linear softmax attention within a single layer?
Mixing them even more finely.
Exactly. It's an active research area. The goal is to dynamically combine the long-range efficiency of linear attention with the precise local modeling of softmax attention all in one block. The challenge: integrating these fundamentally different mechanisms, one global approximate, the other local exact, while maintaining computational efficiency and trainability. The potential reward, though, is an even more efficient and capable architecture that dynamically allocates resources based on context, further blurring the lines, maybe leading to a truly unified attention mechanism. The whole field seems to be moving towards a synergistic combination rather than a single monolithic approach.
So what does this all mean for you, the expert grappling with the cutting edge of LLM development? This deep dive into gated delta networks reveals a truly significant advancement in efficient sequence modeling. We've seen how it effectively unifies the adaptive memory control of gating from Mamba2 with the precise, targeted updates from the delta rule of DeltaNet. The result: a model that consistently outperforms its predecessors across a comprehensive suite of benchmarks, language modeling, common sense reasoning, in-context retrieval, both synthetic and real-world, and challenging long-context understanding tasks. It truly pushes the envelope for linear transformers, offering a powerful alternative to the quadratic scaling of traditional attention.
And connecting this to the bigger picture, the meticulous development of that hardware-efficient chunk-wise training algorithm means gated DeltaNet isn't just theoretically sound, it's robustly and practically deployable on modern hardware. That's crucial for anyone working at scale. Theoretical gains mean little without efficient implementation, right? Furthermore, the extensive exploration of hybrid architectures, combining gated DeltaNet with SWA or Mamba2 layers, shows a clear, compelling path to even higher training throughput and overall performance. These hybrids strategically address the inherent limitations of fixed state sizes and the nuances of local context modeling that even advanced linear recurrent networks can struggle with alone. This represents a crucial, non-incremental step forward in building more capable and efficient LLMs for the future, particularly for applications needing both long-range memory and precise information retrieval, all without those prohibitive quadratic scaling costs.
The gated DeltaNet presents a compelling case for the power of combining seemingly distinct yet complementary mechanisms to solve complex problems in AI. It's not always about inventing an entirely new paradigm, is it? Sometimes it's about intelligently synthesizing and meticulously engineering powerful existing ideas. So as you reflect on this deep dive, consider this. How might the principle of dynamically combining complementary, well-understood mechanisms rather than inventing entirely new ones accelerate progress in other areas of AI research, beyond just sequence modeling? What other pairs of powerful ideas are waiting to be unified in such an elegant and effective way? We hope this deep dive into gated delta networks has provided you with valuable insights. Keep exploring, keep questioning, and keep innovating.